Hello, everyone. Thank you for the previous talk. I think it has been very clear, very comprehensive, and also very inspiring for future developments. Now, what I'm going to do is presenting a little bit of the work that we are doing at ETH in the Safari Research Group on understanding real processing in memory architectures and what kind of workloads are more suitable for these architectures. So this is why the title of this talk is Understanding the Potential of Real Processing in Memory for Modern Workloads. My name, as you can see in the slide, is Juan Gomez Luna, and I work with Professor Mutlu at ETH as a senior researcher. In our group, we have been doing processing in memory research for several years. Processing in memory has already been introduced in the previous talk. It's a computing paradigm that advocates for memory-centric computing systems where processing elements are placed inside or near the memory arrays. Real-world PIM architectures are becoming a reality, and the first one to happen was the ABUMPIMP PIM architecture that brought all of us today here. But there are also some prototypes from Samsung, from SK Hynix, or from Alibaba. And one thing that we notice is that all these PIM systems have some common characteristics. First of all, there is a host processor, either a CPU or a GPU that has access to a standard main memory and PIM-enabled memory. The PIM-enabled memory contains multiple processing elements with high bandwidth and low latency memory access. And these processing elements are relatively wimpy, running at only a few hundred megahertz, and a small number of registers, and maybe a small hash or scratchpad, or maybe they don't even have them at all. And they likely need to communicate via the host processor. There is no direct communication channel usually. This is how one of these state-of-the-art PIM system looks like. At the top, you can see the standard main memory. Here is the host processor, and then we have the PIM-enabled memory with memory arrays and nearby PIM processing elements. As I said, in our work, we have been working with the ABUMPIMP architecture, as Julien and Jean already introduced. This is composed of general-purpose processing cores that are called DRAM processing units or DPUs. Each of them can run up to 24 PIM threads that are called tasklets, and they support 32-bit integral arithmetic, but multiplication and division are emulated, as well as floating point operations. Each of the DPUs has access to its own DRAM bank called MRAM, and its own scratchpad that is called DRAM. And this is how the system looks like with the current ABUMPIMP system with 2560 DPUs with the dual-socket CPU, DRAM beams, and PIM-enabled ones. And I think I can go very quickly over this. This is how the system looks. Let's say the general overview with the main memory, the host processor, and the PIM-enabled memory. And inside the PIM-enabled memory, we have ABUMPIMP DIMMs, each of them with PIM chip. And inside the PIM chips, we have the DRAM banks and the DPUs. I can go quickly over this because it has been introduced before. So we started the collaboration with ABUMPIMP back in, I would say, 2019 or something, even before the first generation was released. So our first experiments and analysis were with the FPGA emulator. And since then, we have been trying to do two main things. First of all, understanding the system itself, understanding the architecture itself, and second, figuring out what are good workloads, suitable workloads for this architecture. So in our first paper, we did a lot of, I'd say, architectural analysis of the ABUMPIMP DPUs. And one thing that we realized by doing this sort of roofline model, as you can see here, we are comparing we are representing the arithmetic throughput over the operational intensity. Each of these dots corresponds to the number of tasklets or PIM threads that we have used. So one of the first thing that we notice is that there are two regions, the memory bound and the compute bound region. But interestingly, the throughput saturation point, that is the transition between the two regions, happens at a very low operational intensity. For example, this is for 32-bit integer addition, And here we notice that just with one integer addition per every 32-bit element, we are in the compute boundary. This was really interesting to us because we have been working on architectures that have been traditionally memory bound. The biggest issue was in the access to the memory, to the off-chip memory. Now we find an architecture that is fundamentally compute bound. So this is interesting because on the one hand, the memory bound bottleneck or the data movement bottleneck is solved, at least for some access patterns, streaming access patterns. And on the other hand, that means that if you optimize your code, you make your code run less instructions, then it will go faster for sure. So that's something really interesting. As I mentioned earlier, we have worked on processing in memory for a long time, writing multiple papers and also book chapters like this one, where one of the things that we cover and discuss are potential barriers to the adoption of processing in memory. And the first one, as you can see, is applications and software for processing in memory, or understanding what workloads are really suitable for processing in memory systems. And that's what we have been doing, as I said, and that's what I want to present today. The first thing is coming from our first paper related to the ABUMPIMP architecture. Not only we analyzed the architecture itself, but also did a benchmarking and workload suitability study, and that led us to create a benchmark suite called PIM, a common set of workloads that can be used to evaluate the ABUMPIMP PIM architecture, compare software improvements and compilers, and compare future PIM architectures and hardware. We had two key selection criteria. First of all, workloads from different domains, and second, workloads that are memory bound in conventional processor-centric systems. In total, as you will see, there are 16 different benchmarks. In total, 14 different workloads because we have two versions of two workloads. And this is the entire list of workloads. As you can see, we have things like dense linear algebra, sparse linear algebra, databases, data analytics, etc. We did a lot of analysis of these. So first of all, showing that all these workloads are highly memory bound. They all fall in the memory bound area of the roofline of an Intel Xeon CPU, and they are diverse in terms of memory access patterns, sequential, strided, random operations, and data types, and communication and synchronization needs. I will not show, of course, all the details of this analysis today because I have been covering lectures and talks about the PIM benchmarks, but I just want to give you like a key insights, let's say, of this analysis. We did the analysis of the 16 PIM benchmarks on two ABUMPIMP-based PIM systems, the larger one and an older one with just 64, well, I don't remember how many DIMMs, I think 10 DIMMs, in total 640 GPUs. There we run strong and weak scaling experiments on one GPU, on one rank, and up to 32 ranks, and also compare the performance to state-of-the-art CPUs and GPUs. I will go directly to this comparison to CPU and GPU. You can see that we classified the 16 workloads in those that are two classes, let's say, one of these of those that are more PIM suitable or more ABUMPIMP suitable workloads, and less PIM suitable or less ABUMPIMP suitable workloads. This plot represents the speed up over the CPU. That would be this blue line, right? So more PIM suitable workloads are those that fit. So those that fit better the ABUMPIMP PIM system and overcome and outperform the GPU. So these ones here. These ones, so for these 10 PIM benchmarks, we see an average performance improvement of 2.54 times with respect to the GPU. The GPU was an NVIDIA Titan 5. And also for the smaller ABUMPIMP system that I think is no longer available or commercialized, but at least we could see that the performance was within 65% of the performance of the GPU. And the interesting observation here are the three key characteristics that make these workloads more suitable for the ABUMPIMP system. First of all, they use streaming memory accesses. Second, there is no or little inter-DPU synchronization. Remember that there is no direct communication channel between DPUs. And third, there is no or little use of integer multiplication, integer division, or fault equal operations. Those are costly because they are emulated. If one workload has these three characteristics, then it's potentially suitable for the ABUMPIMP architecture. I would say that these are the most desirable workloads. That doesn't mean that we cannot get performance improvements for other workloads that also have random access patterns or straight access patterns. But this is like the most desirable workload, the most desirable characteristics for a workload. Just as a summary, here you can see some comparison for the CPU and the comparison to the CPU and the GPU. As you see, more than 23 times faster than the CPU for the 16 PRIM benchmarks, and 2.54 times faster than the NVIDIA Titan 5 for 10 PRIM benchmarks. We published these in the IEEE Access Journal, but there are also shorter versions in arXiv and longer ones as well. And everything is publicly available in our repository, so there you can access micro benchmarks, and scripts that we generated. And as I said, I have delivered multiple lectures and talks about these PRIM benchmarks. So here you can find a link to walk through the rest of them. So that we continue doing the analysis of what kind of workloads are more suitable for ABUMPIMP PIM architecture. And the first thing that came to our mind was expanding our analysis of the sparse matrix vector multiplication. SPMB was already in the PRIM benchmarks, but it didn't perform very well, so we wanted to see what was wrong there or what would need to be modified in the implementation in order to get better performance. And that's what led us to do this SparseP library, a library for sparse matrix vector multiplication on real PIM architectures. I will go pretty quickly over these slides. There are also talks available. As you see, also the paper is available in arXiv. The repository is open source. So the idea is to do a comprehensive characterization of SPMB on the first real commercial PIM architecture, that is ABUMPIMP. SPMB, as you already know, is a highly memory-bound kernel. So in principle, very suitable one for PIM architectures because PIM architectures can overcome this data movement bottleneck. Well, in the end, we generated 25 different SPMB kernels, as you see, with four compressed matrix formats, like CSR, COO, block CSR, and block COO, 6 different data types, different partitioning techniques, load balancing techniques, and synchronization approaches. And on our comprehensive analysis with many different sparse matrices, 26 different sparse matrices with different characteristics, sparsity, degree, etc. This is the system that we consider for SPMB. We have the main memory, we have the CPU in between, and we have the PIM-enabled memory. So first of all, we need to load the input vector to the PIM-enabled memory, then execute the kernel on the PIM-enabled memory, and finally retrieve the results, maybe partial results that will be later merged in the CPU. So I'm showing these because our experimental results have considered all these steps, not only the execution in the kernel, because in the end we have to take into account that there is still data movement here because data resides in the main memory, originally resides in the main memory. And that's also something to take into account when it comes to selecting what's the most appropriate or the most beneficial implementation of SPMB for a specific operation, particular SPMB on a specific matrix. Okay, so as I said earlier, we have explored different data partitioning techniques, 1D partitioning and 2D partitioning. For example, in 1D partitioning, we perform the complete SPMD computation only on the PIM cores. That's nice because we won't have to merge results in the host, but that also means that we need to transfer more data between the CPU and the DPUs. In the case of 2D partitioning, we will have to do some merging of the output vector in the host CPU, but at the same time, we are trading off computation versus data transfer. We won't spend so much time on data transfers. And in 2D partitioning techniques, we try equally sized tiles, equally wide tiles, and variable sized tiles. We also explore different load balance techniques or load balance approaches across threads. For example, balancing the rows between different threads in 1D partitioning and also in 2D partitioning, or balancing non-zero elements in both 1D and 2D partitioning. So, and also synchronization approaches, like coarse grain or fine grain. As you see, the difference here is that we're going to have either one single log for the entire output vector or multiple logs for the output vector, and then a log-free approach as well. So as I said in the beginning, in total 25 different sparse matrix vector multiplication kernels with different instruction formats, different data types as well, and very comprehensive analysis. I don't have many results here, just this comparison of 1D and 2D partitioning for different matrices, those that are regular and those that are more scale-free. So as you can see, in general, 2D equally sized partitioning is better for regular matrices than 1D partitioning. It happens exactly the other way around for scale-free matrices. But there is also one more interesting observation here, is that we are not using all cores in all these cases, because it's in the end, remember, we are considering the data transfer from the main memory to the PIM-enabled memory, computation in the PIM-enabled memory, and then moving the results back to the main memory. So that's also something to take into account. So that the data transfer costs are also something to take into account when optimizing the overall execution on the system. That's why we decided to keep some cores idle in order to obtain the best overall performance. We also did a comparison to CPU and GPU. In this case, I think it was it was a NVIDIA V100. As you see, they are very different systems, right? CPUs and GPUs can be called processor-centric, PIM or ABUMPIMP can be called memory-centric, and there is where its biggest advantage resides, the large memory bandwidth. You can find all the detailed analysis in the paper, but here, one thing that I would like to highlight is this comparison, right? For the kernel only, the PIM system was able to achieve more than 50% of the peak performance of the DPUs, while CPUs and GPUs don't even reach 1% of their peak performance. So they are heavily imbalanced, right? With respect to this kind of workload that is so important and so useful. So what this basically means is that PIM systems are able to better balance compute and memory access, at least for this kind of application. And I think that this is a really interesting observation. The truth is that the end-to-end performance was not that great. In the end, CPUs and GPUs still have good bandwidth and much higher performance, peak performance. This is a comparison also for 32-bit floating point numbers that are not natively supported by the PIM system. So probably this is the worst case for the PIM system, and that's what makes this large performance difference. But still, the PIM system is more energy efficient than the CPU. As you see, 38% more efficient. Anyway, you can find many more details in the paper that was published on Metrics last year. And there are lectures as well, and the code is also publicly available. More recently, we have worked in genome sequence alignment in the context of the BioPIM project that Jan mentioned earlier. This work called high throughput sequence alignment using real processing in memory systems was published in the Bioinformatics journal. And here we are focusing on the well-known sequence alignment algorithms like Smith-Wunsch, Smith-Waterman-Goto, GenAsem, and the state-of-the-art waveform algorithm for sequence alignment. One thing that we needed for a start is to have a good motivation, and the motivation is that these workloads are memory bound. That's something we show in the paper by analyzing how the sequence alignment scales on these algorithms scale on the CPU. So this is execution time for different number of CPU threads for Middleman-Wunsch, Smith-Waterman-Goto, GenAsem, WFA, and a version of WFA that's called WFA adaptive. As you see, in all cases, performance saturates. So that clearly shows that that these are memory-bound workloads. And this is we have a perfect motivation for processing in memory for ABUMPIMP PIM, and we came up with this framework that can be adapted to any of these sequence alignment algorithms or others, newer ones that could appear. What we are basically doing here is, first of all, we are loading the input sequence pairs from the one input file and SSD to the main memory. Then we need to transfer the sequences to the MRAM in the multiple DPUs that we are going to use. And at that point, or when the transfers are done, we can launch the kernel execution on the DPU, accessing or copying, first of all, copying sequences from the MRAM to double RAM, and then performing the computation using different threads. So the approach that we follow here is like, let's say, embarrassingly parallel, in the sense that each individual thread is working, each individual thread in the DPU is working with a different sequence pair. So in that sense, it's good for performance because we don't need to synchronize, but at the same time, it also imposes some limitations on what's the maximum length that you can process, right, for the sequence pairs. But anyway, we keep working on developing more sophisticated approaches as well. At some point, we will be done with the alignment, and we copy the results back to the from the MRAM to the main memory, and then we can save the results in an output file if we want. Okay, so we evaluated these using real and synthetic data sets, as you can see, for with different read lengths and also different edit distances. We evaluated the ABUMPIMP system with 2560 pin cores and 3 CPU systems. We didn't use GPU here because there was no GPU implementation of all these workloads that we used back then when we were working on this project. Now there are some, and we compared the 3 different CPU systems. As you see, they have relatively different characteristics. The one interesting one is this last one, third one, because it has the largest L3 cache. So, and actually that's one other thing that shows that these are memory-bound workloads is the fact that the fastest one is the one not with the largest number of threads, but the one with the largest L3. So in the end, memory-bound workloads benefit from largest on-chip memories, right? If we compare to the ABUMPIMP, including the data transfers, we see already really interesting performance improvements from up to, for example, 2.56 times faster for WFA adaptive, and this is including the transfers. Without the transfers, that maybe we will see in some future system where the standard main memory becomes pin-enabled memory as well. We could see more than 25 times performance improvement. This is just some suggestion that the overhead of these transfers could be avoided or hidden by making the bindings as main memory or overlapping data transfers for computation. That I think is something that it's probably in the roadmap of ABUMPIMP according to the previous presentation. I have some more insights here. PIM does not outperform CPU for algorithms with regular access pattern and mode length. And here we have more analysis for WFA and WFA adaptive. But I prefer to go quickly over this just to show you some comparison to the GPU. We compare to the GPU implementation of WFA that was released with this paper was under review, and as we can see, most of the cases PIM outperforms the GP. You can find more details in the paper. Source code is also publicly available, and we also have lectures about this. And just to conclude, I want to also show you one recent work that is called TransPIM. It's a library for efficient transcendental functions on processing in memory, on ABUMPIMP processing in memory. We published this year in Sparse conference, and this is well, the question that we had is what can we do to run transcendental functions on the PIM system? The PIM hardware is relatively weak, wimpy, not many different instructions, not sophisticated arithmetic units. But transcendental functions are important in many real workloads, even in workloads that are memory bound according to other analysis, prior analysis that we made. And so we thought that there were three possible alternatives. The first one, if you find this transcendental function in your PIM core execution, would be, and this would be the ideal one, to have one transcendental unit on the memory side. So the PIM kernel would call this transcendental unit, run this transcendental function, or calculate this transcendental function pretty quickly, and then continue the execution of regular arithmetic instructions in the PIM core. That would be ideal, but doesn't exist. What definitely exists is that you can finish or freeze the execution of the PIM kernel on the PIM core, move data back to the CPU, compute on the CPU, and then return the control to the PIM core to continue the execution of the PIM kernel. Or the third alternative, which is what we actually did, is creating a library of transcendental functions that is called TransPIM. So the transcendental function can be calculated using different methods in the PIM core itself. And our open source library includes methods based on CORDIC, based on lookup tables for trigonometric functions, hyperbolic functions, exponentiation, algorithms, square root, etc. As I said, we have used CORDIC, which is an iterative method that uses bit sheets, addition and lookup tables, table lookups. Basically, the rotation mode computes the function by rotating a vector iteratively until we are as close as we want from the accurate result. And the rotation is done by multiplying a vector or a matrix. The matrix represents the rotation angle, and this decreases in every iteration in order to fine-tune the result. Or we can use FATSI lookup tables to obtain an approximate output, and we can combine these with interpolation. If we access to entries from the lookup table, and then we use this interpolation equation. In total, TransPIM supports all these different functions in its current version for all these different implementation methods. As you see, there are CORDIC, and then several methods based on lookup tables and interpolation, and even one method that combines both. So for some of them, or actually for the sine function, we generated all different methods. Then for the rest of them, we generated those that appear to be more suitable. And yeah, that's it. We have many results for analysis of the different methods in the paper, but here I just want to show you some comparison for real-world benchmarks to CPU. These are results for Blackstone, this benchmark from the Parsec benchmark suite. We are comparing here one CPU core, 32 CPU cores, and then 4 different implementations. On the PIM side, even this one, polynomial is a PIM baseline. It's using polynomial approximation, and these are 3 different methods using TransPIM. As we see, well, it's significantly faster than the execution of one CPU core, and more or less on par with 32 cores. Even this version that uses fixed point representation, that is more suitable for ABUMPIMP, that doesn't support floating point numbers, is even faster than the 32 thread GPU baseline. And we also have results for sigmoid and for softmax that are widely used activation functions in machine learning. The results are not, we are not really outperforming the execution on 32 CPU cores, but we are pretty close, and in the end, the benefit is not coming from the direct comparison, but coming from the ability to save data movement, which is one of the key motivations or the main motivation of cross-linear memory systems. So if you compare this B scenario and the C scenario that I presented in the beginning, you'll see that you can achieve really interesting performance improvement, even though the execution of the transcendental function itself is not that fast on the B core. So this is links to the archive version of the repository. As I said, it was presented at Sparse. Source code is publicly available, and we also have longer talks about this. This is like a very brief summary of many of the things that we are doing with the ABUMPIMP PIM system. As Jan mentioned earlier, we will have a later presentation with Sylvain on some joint work on ML algorithms that will be after the break, I believe, or in the afternoon. But yeah, we keep working. We just got 2 papers accepted. One is let's say the first exploration of homomorphic encryption on the ABUMPIMP PIM system. It has been accepted as a poster in the ETH Zurich conference, and the other one is a high-level programming library for ABUMPIMP as well that is called SimplePIM, and this will be presented in PAC conference in October, and hopefully we will release the library as well for people to use. And even though I always say when people ask me, is it difficult to program the ABUMPIMP system, I always say it's much easier than programming a GPU, and we have been learning GPU programming for more than a decade now. But I think it's gonna be even easier to program it using our library that, as you will hopefully see, it can even outperform the performance of some of the PIM benchmarks from the hand-tuned version, because it's applying, let's say, additional optimization tricks. From the industry, we have been organizing tutorials in HPCA, in ASPROS, in ISCAN, the next one, which will be fully virtual on October 29th, and the micro conference, and I think that's all. So thank you for your attention, and